Okay, in this chapter, we are going to talk about the Fibonacci sequence. But one kind of very interesting story is Fibonacci sequence is not done by Fibonacci, actually. Fibonacci actually did several things, amazing ones. And he was born in 1175, around 12th centuries. Uh, but one of the things he did was like recognize the greatness of Hindu-Arabic decimal systems, including zero and everything, and he introduced that, okay, in his book. And he also find out the solutions for such like this kind of cubic equation. It's not any style like rational number, something like that, right? So he did many amazing things. But eventually, the around 19th century, Eduardo Lucas used his name when he explaining the following stuffs, right? And eventually that's kind of explained in this format. So you can start with a pair of adults, rabbit, and in the very next month they have a pair of young rabbits, right? And these rabbits never die. Okay? So then we just count every month how many rabbits we have, right? So at the first month, the original adult pair and young pairs of these rabbits. So we have two pairs of rabbits, right? The next month, actually, this young pair of rabbits becomes adults, but they only just grow up. They don't have any babies anymore, not yet. But this young pair should have one babies, right? So a pair of babies. So total is two pairs of adults and a pair of young rabbits, right? So altogether, it's going to be three. And the next month, these two adult pairs of adults becomes adults, and these young pairs becomes adults, and these two pairs got two pairs of young rabbits total, right? Each pair got one pair, right? So altogether we have five pairs of rabbits. So you can see how it's going to work, right? So for example, in this 8 months, we are going to have 21 plus 13 adult rabbits, right? Altogether. So we have 34. But at the same time, we have that 21, okay, we'll have 21 babies, right? Actually, pairs, but like that. So altogether, we just need to add this one. That's the total 55 rabbit, a pairs of rabbits, right? So we are going to get this one. So you can see how it's going to work, right? So and at the same time, these numbers becomes like that, right? Because we're just adding them. So next one is going to be 55 at 9th month, and we can calculate like this. So we can make some kind of formula out of this one. So let's say this is F1, and if you're not really matching the number of months and this index, then this column is better. So that is F1, the first month, and F2, the second month, and F3, F4, like that. And those numbers are actually the sum of previous two consecutive terms, right? Adding these two is the 1. 1 plus 2 becomes 3. 2 plus 3 becomes 5, and 3 plus 5 becomes 8, like that, right? So F1 plus F2 equals F3, and F2 plus F3 equals F4, and F3 plus F4 equals F5. So in general, we can think Fn minus 2 plus Fn minus 1 equals Fn. So no matter what this number is for index, all we need is two previous values. So when you define any Fibonacci sequence Fn, this is the typical kind of way to define it. Okay, so now let's look at here. there are many interesting stuff happens in this Fibonacci sequence, and one of them is any two consecutive Fibonacci sequences are relative prime, which means there is no common factor. Right? That's very strange, right? When you look at those, just to check any two consecutive numbers, 3 and 5, no common factor. They are relatively prime. How about 13 and 21? And 21 and 34, 34 and 55. Doesn't matter which two you choose. If they are consecutive numbers from the Fibonacci sequence, then they are relative prime. Okay, the proof, we need Euclidean algorithm again. So for any n, let's just choose any n, we can have Fn equals, by the formula, is Fn minus 1 plus Fn minus 2, right? Then let's change the format, looks like this. F sub n minus 1 is same as 1 times Fn minus 1 and Fn minus 2. So it looks like we have Q times B plus R1. So let's treat that one as this Fn. If you divide Fn by Fn minus 1, then quotient is 1 and Fn minus 2 is a remainder, right? So next one is, let's go down one more, Fn minus 1. Then it's 1 times Fn minus 2 plus Fn minus 3. If you go further, Fn minus 2 is 1 times Fn minus 3 plus Fn minus 4. So we just keep doing that. Then at the end, F3 is 1 times F2 plus F1. So when you look at this one, this is really the format of Euclidean algorithm, right? Because it looks like we try to divide this divisor of the previous term by the remainder of the previous term, right? And keep doing that. And keep doing so like this. Which means by that Euclidean algorithm, we can think the greatest common divisor of the first two terms, right? Fn and Fn minus 1, right? Those two, the same as greatest common divisor of Fn minus 1, Fn minus 2, which is equal to greatest common divisor of Fn minus 2, Fn minus 3. And we can keep doing it. So at the end, this greatest common divisor must be equal to greatest common divisor of F2 and F1, right? Which is 1 and 1. Okay? So it should be 1. So what does that mean? We start with just the arbitrary n, right? So any two consecutive Fibonacci numbers is relatively prime because the greatest common divisor of those two numbers is 1. Eduardo Lucas also find very interesting results from this Fibonacci sequence. One of them is when we adding up all these Fibonacci sequence numbers from F1 through Fn, that's actually same as Fn plus 2 minus 1. So please check with the table for the few cases, but let's just prove this one in general case. Okay, so let me start this way. F1 is, let me state this way, because F3 equals F2 plus F1, right? Which means F1 is F3 minus F2. And F4 is F3 plus F2, which means F2 is F4 minus F3, right? So we just keep doing it. Then Fn plus 1 is Fn plus Fn minus 1, which means Fn minus 1 is fn plus 1 minus fn. And lastly, fn plus 2 is fn plus 1 plus fn. So fn is fn plus 2 minus fn plus 1. Right? And we are looking for the sum of f1 through fn, right? So let's just adding this. And the left hand side becomes f1 plus f2 plus up to fn, right? And the right hand side, this f3 cancel out with f3 and f4 with f4, right? We know that, so keep doing it, cancel out this one. And lastly, fn plus 1 cancel out with fn plus 1, remaining only this and that terms. So the right hand side becomes f sub n plus 2 minus f2. And what is f2? It's 1, right? So that's the proof of this equation. Okay, and there are many interesting stuck. Okay. There are many interesting steps in Fibonacci sequence once again, and one of them is this one. Okay? So no matter what n we have, the fn squared is actually a product of its previous one and the next ones, and like negative 1 to the n minus 1. So it could be plus 1 or minus 1. That's all. Okay. So please check several examples from the table, right? But in here, I only just give you the proof of this one. Okay. So first of all, let's say when n equals 2, then f2 squared is actually 1 squared, which is 1. And fn minus 1 is 1, and fn plus 1 is 3. So it's 1, and let me just do all together. So it's negative 1 to the n is 2, so n minus 1 is 2 minus 1. So altogether, it's 1 times 2 plus negative 1 to the 1 is negative 1. So it becomes 1, which means they are equal. So we found that this equation is true when n equals 2. Second, let's just suppose this equation is also true when n equals kind of n minus 1 case, right? So let's say fn minus 1 squared is fn minus 2 times fn plus negative 1 to the, now be careful, is n minus 1, but right now our n is actually n minus 1, so n minus 1 minus 1, right? So we can say, let me rewrite again, fn minus 1 squared equals fn minus 2 fn plus negative 1 to the n minus 2, right? So let's just accept that. Okay? Let's just assume it. And as you can see, we are just using mathematical induction here. Then let's try to calculate what is fn minus 1 times fn plus 1. This one, right? Then by formula from Fibonacci sequence, that fn plus 1 is actually sum of fn minus 1 and fn, two previous consecutive terms, right? Then by distribution law, the same as this one, right? When you multiply. Then we already have fn minus 1 squared like this. So let's just substitute in that part here. Fn minus 2 times fn. And let me write down this one at the end. So put fn minus 1 times fn and negative 1 to the n minus 2. So altogether, when you look at this, fn is a common vector. So you can put fn minus 2 plus fn minus 1 times fn plus negative 1 to the n minus 2. Then this one is fn minus 2 plus fn minus 1 is same as just fn, right? By the Fibonacci sequence definition, so it's fn squared plus negative 1 to the n minus 2. So from this, you can say fn squared itself is just fn minus 1 times fn plus 1 minus negative 1 to the n minus 2, which is same as fn minus 1 times fn plus 1 plus is negative 1 times negative 1 to the n minus 2. Right? So that is simply negative 1 to the n minus 1. Right? We have one more negative, right? So we have to increase 1 for the exponent value. So this is that equation. Right? So that's the proof for here. But when you look at that one for the even case, like when n equals even, then we'll have that, and this term, because n is even, is always odd, so we are going to have always minus 1 there, okay? So eventually we are going to have this one. It's nothing new, it's just the even number case of these general forms, okay? Now from there, we could have the following nice tricky puzzle. So you might see this one before. Like we have some nice square. Each side is 8 and 8, right? So 8 by 8 square. And we just cut this paper like this and rearrange it. Okay? So this portion goes here. And that one goes here. They're actually exact identical shape, right? And these two goes here and here. And because that is 3 and this is also 3, so they're going to match really nicely, right? Over here, 3 and 3, right? So this triangle is a right triangle with 3 and 8. So that's 3 and 8 here. Okay, and this trapezoid goes to here. Like a 5, 5, and 3. So 5, 5, and 3, right? So it's really well arranged of the same objects, right? Like that. But when you calculate the area, the original one is 8 by 8, right? So it's going to be 64. Over here we have 5 plus 8 is 13, right? And this is 5. So 13 times 5, 65, right? Okay, so like, what the heck, right? I mean, we didn't add anything or delete anything, but it looks like we have a different area. Okay? So what's going on, right? So one of the possible explanations for this one is when you look at this triangle, this small one, and look at this bigger one, and in these arguments, it looks like we are talking about the similar triangles, but actually they are not. Simply, we can think like this, because it's 3. So what is the ratio or the slope of this line? Okay, so it's 8 over 3, right? That's the ratio. Then if we have exact same similar triangle over here, then the ratio between this side and that must be also same as that. So 8 plus 5 over 5, right? Okay, but that is 13 over 5. And definitely it's not equal to the ratio. Because when you by the cross multiplication, you have 40 equals 39, right? It's not same number. So these ratios are not same. So what really happens here is when you magnify in this area, then you have slight gaps actually. Same thing over here too. And that area is just 1 compared to 65 or 64. So in human eyes, it's a little bit difficult to find that gaps, right? And if you try to do this one with paper cutting and arrangements, it's more difficult, right? You cannot really cut that much well, right? So how can you explain? Yes, one way is using these ratios of similar triangles. Another one is by this Fibonacci sequence. Can you see that? Those numbers we use over here is actually here. So for some even number, we are going to get 8 for Fibonacci sequence, right? So this is 8 squared. And over here we have 13 and 5. That's one of them is like this, the other one is like that, right? So like when do you get 8? It depends on how you look at it, right? But in this case, it should be 6, right? So when n equals 6 case, right? Which is 2 times 3. So that is F5 and that is F7. Then multiplying those two Fibonacci numbers is actually 1 greater than the square of Fn. Right? So we can explain using this, okay, why these two the areas of these two figures are not same. So next example is make your own very similar puzzle, right? So you don't need to touch anything. This cutting method and everything should be exact same, but the numbers must be different, right? So some other cases, right? So please do, please enjoy that. Okay, in this example, we are going to show you the relation between the Fibonacci sequence and golden ratio. And yes, we can get the golden ratio from the Fibonacci sequence. Okay? So let's start with to make another sequence. Is actually the ratio between two consecutive Fibonacci sequences. So let me write down that one first. F1 is 1, F2 is 1, F3 is 2, 3, 5, 8, 13, 21, and blah blah like that, right? Then P sub n is f of n plus 1 over fn, right? So Pn is the next term over this one. So it's going to be 1, right? So it's P1. So P2 is 2 over 1, which is 2. So P3 is this one over that. So 3 half. And P4 is 5 over 3. And P5 is 8 over 5. Can you see that? Right? Always the next term over that same indexed Fibonacci number, right? I find that, right? So this table is just a collection of those, right? So as you can see here, P3 is going to be 3 half, right? So it's going to be 1.5. So please calculate each of these P sub 6, P sub 9, and P sub 10, right? Just for checking. Then when you do further of this one, then eventually it starts from 1 and goes to 2 and 1.5 and go to 1.666 like that and going down 1.6 and 1.615, 1.619. So like it's kind of oscillate a little bit and eventually it's approaching to a certain number, right? So when you take the limits of this, when n approaches infinity, then what is going to be the limits of this sequence? And we are going to claim that limit is the golden ratio. Okay, so for that, first, let's just prove this. In this new sequence, Pn, we calculate this one, okay, keep doing it. Then, if you choose any Pn, then that is actually 1 plus, we sprinkle up previous value. So, let's just prove it. Pn, by that definition, is same as Fn plus 1 over Fn, right? Then Fn plus 1 is, by the definition of Fibonacci sequence, is Fn plus Fn minus 1 over Fn. Then we can put this one separately, so Fn over Fn plus Fn minus 1 over Fn. So it's 1 plus Fn minus 1 over Fn, or when you take the reciprocal of it, it's 1 over Fn over Fn minus 1, right? But when you look at the definition of that P of n, P sub n, here, if you just reduce by 1 for those indexes, then this one is same as P sub n minus 1. So altogether, it's 1 plus 1 over P sub n minus 1. Okay, so that's the proof of this one. Then let's just look at that case, right? We just find out Pn is same as that, right? So how about let's take limits of it, right? So right now we want to skip that one, but eventually this sequence goes to a certain number, right? So whatever the number is, let's call that is phi, okay? So which means the limit of this p sub n when n approaches infinity is phi, whatever the number is, right? And let's find the exact value of that number, phi. So what is really this phi is? Then when you look at the sequence, by the definition of phi, we know this, right? Whatever the number is. But when you start one less number of the sequence, what is going to be eventually the limit of the sequence? Still same thing, right? It's only depending on where you start, right? If the original will start from here and looking for the limit, you just start one time later or slower or faster, doesn't matter, right? Eventually, it doesn't matter where you started. If you keep this sequence as it is, then the limit must be same, right? Therefore, we are going to get same phi from this one. So, from that expression, let's just take the limits as n approaches infinity. Then the left-hand side is phi, right? On the right-hand side, when you take the limits of 1 plus 1 over p sub n minus 1, by the condition of limits, we can put this limit for each one of them, right? Of course, we need some condition, like they has limit or something like that. There is no n, so limit of 1 is just 1, right? You stay 1 like that. And over here is a fraction, right? Then you put this limit for numerator and denominator. Numerator is still 1, so let me just skip that part. But put this limit only p sub n minus 1. Then as you can see here, that limit is also same as the original ones, like a phi, right? So when you look at that together, phi equals 1 plus 1 over phi, right? So let me multiply phi on both sides, because clearly phi is not going to be 0, right? It's just between 1 and 2. So multiply phi is okay. Then phi squared equals phi plus 1. Or phi squared minus phi minus 1 for 0. Then by the quadratic formula, phi is negative b plus minus square root of b squared minus 4ac over 2a, right? So it's 1 plus minus square root of 1 plus 4 over 2, which is 1 plus minus square root of 5 over 2. But once again, we already knew that the limit p must be positive, right? Clearly, because everything is just a ratio between two positive numbers. So this negative is next, right? So therefore, p must be 1 plus square root of 5 over 2, and that's approximately is 1.61 something, and that is the famous golden ratio. So it's TI. Okay?